On November 12, 2025, a ripple passed through the fabric of spacetime, triggering alarms at 3 gravitational-wave observatories. The signal, catalogued as S251112cm, stopped astrophysicists cold. Its chirp mass indicated an object weighing less than our Sun. No known stellar process produces a black hole that small. Stars that collapse at the end of their life cycle leave remnants several times the Sun's mass, at minimum, dictated by the Tolman-Oppenheimer-Volkoff limit. Something this light has only one mathematically sound origin. It is a primordial black hole, an object formed not from a dying star, but by collapsing directly from the extreme density of the universe itself during the QCD epoch, fractions of a second after the Big Bang. Subsolar black hole mergers are exceptionally rare. Finding a single candidate across more than 4 years of gravitational wave observations matches the predicted distribution models where primordial black holes account for the universe's total dark matter content. The S251112 centimeter detection provides the first observational evidence for a mechanical framework where primordial black holes define the origin of all cosmic matter. Cosmology wrestles with a dual paradox. The first half is cold dark matter. It constitutes roughly 85% of all matter in the universe, exerting immense gravitational influence while remaining completely undetectable through electromagnetic means. The second half is baryogenesis. This is the unresolved mechanism explaining why the universe contains a vast abundance of normal matter, baryons, and almost zero antimatter, despite physics demanding they should have been created in equal amounts. This split-screen diagram visualizes the massive gap in the cosmic energy budget using Planck 2018 data. The cold dark matter density fraction sits at 0.265, while the normal baryon density fraction is a much smaller 0.049. Recent research by physicists at the University of Geneva proposes that primordial black holes resolve both the dark matter density problem and the baryogenesis asymmetry problem simultaneously. The math hinges on mass. The most massive primordial black holes from the early universe possess enough gravity to survive to the present day, acting as cold dark matter. Conversely, the lower mass primordial black holes completely evaporated in the early universe. The specific mechanics of their decay generated the observed asymmetry between matter and antimatter. The life cycle of primordial black holes, from early universe evaporation to late universe gravitational stability, governs the exact ratios of dark matter and visible matter observed today. To test this theory, we have to evaluate the statistical distribution of black hole masses. Early models often relied on a monochromatic population, assuming primordial black holes all formed at one specific mass. A monochromatic population requires impossibly precise peak masses to satisfy late universe constraints. If the objects are too light, they evaporate entirely and leave no dark matter behind. A polychromatic, or broad, mass spectrum provides a mathematically robust alternative. In a broad spectrum, black holes form across a vast gradient of sizes. The highly massive ones survive until today, successfully accounting for the modern cold dark matter density without requiring artificial fine-tuning. This chart plots primordial black hole mass over cosmic time. Objects lighter than 4 × 10 to the 11th kilograms completely decay. They hit zero, evaporating long before reaching the present day. A broad spectrum naturally accommodates the objects sitting between immediate evaporation and supermassive status. It provides a clean explanation for the surviving subsolar mass observed by the LIGO detection. A polychromatic distribution is a mathematical necessity. It allows the universe to retain heavy dark matter anchors while sacrificing lighter black holes to the evaporation process. The asymmetry between matter and antimatter relies on a core theoretical mechanism, a specific Lagrangian action describing the physics of the early universe. This equation defines a derivative coupling. It bridges the macroscopic geometry of spacetime with the microscopic flow of particles.
The Ricci scalar, R, mathematically represents the physical curvature of spacetime. The baryon-lepton current, J, tracks the net difference between normal matter particles and antimatter particles. In a completely static, unchanging universe, this mathematical coupling remains inert. But the early universe was not static. Its rapid, violent expansion, measured by the scale factor, serves as the necessary catalyst to activate the equation. As the universe expands, the Ricci scalar changes rapidly over time. This highly compressed shift acts mathematically as a dynamical chemical potential. This dynamical chemical potential physically applies a bias to the quantum vacuum immediately surrounding an evaporating primordial black hole. Standard Hawking radiation is perfectly symmetric. Under normal conditions, a black hole emits equal parts matter and antimatter. The extreme expansion of the cosmos forces space-time itself to bias the black hole's evaporation. This interaction permanently breaks the symmetry of the universe. This symmetry-breaking process creates asymmetric Hawking radiation. The chemical potential forces a violation of CP symmetry, exactly as the black hole decays. During this decay, the black hole emits a statistically higher yield of normal baryons compared to antibaryons. When you integrate this slight baryon-lepton charge across the total lifespan of all evaporating black holes in the early universe, it results in a massive net positive volume of normal matter. Researchers test this theoretical framework by tuning the model, balancing the initial density of primordial black holes and the mathematical coupling constant against observed reality. This chart displays the fractional energy density models. In the top panel, solid lines representing primordial black holes curve upward, recovering the exact Planck 2018 dark matter parameter. In the bottom panel, the generated baryons follow a similar curve, recovering the visible baryon fraction. The raw density of dark matter and the abundance of visible matter in the universe are two outputs of the exact same evaporation equation. While the relative density fractions match, calculating the raw baryon-lepton yield requires factoring in the universe's entropy density. If physicists extrapolate the universe's radiation density purely backward, the model's yield falls an order of magnitude short of the strict observational bounds set by Big Bang nucleosynthesis. This graph maps the baryon-lepton yield at present day. The descending purple line tracks the model's yield against effective radiation energy density. The horizontal gray band marks strict observational limits required by physics. The model is viable only where the purple line intersects this window. The model requires that the decaying primordial black holes themselves triggered the cosmic reheating phase. In this scenario, most of the universe's radiation didn't exist until the black holes decayed. This lower initial radiation density changes the timing of the reheating epoch, represented by the scale factor. Adjusting this timing alters the calculated entropy density of the early universe. This brings the predicted baryon-lepton yield into exact alignment with the bounds set by Big Bang nucleosynthesis. Under this model, primordial black holes functioned as the fundamental engine of the early cosmos, simultaneously generating radiation, spawning matter, and stabilizing into dark matter. Theoretical particle physics must eventually be verified by observational astronomy. The November 2025 LIGO detection carries a false alarm rate of roughly once every 4 years. It is a critical piece of evidence, but on its own, it is not total confirmation. Future hardware will settle the math. The European Space Agency's Laser Interferometer Space Antenna, LISA, is designed specifically to detect gravitational waves from the earliest epochs after the Big Bang. On the ground, the proposed Cosmic Explorer facility will operate at 10 times the sensitivity of current interferometers, gathering data at unprecedented resolutions. As these observatories accumulate more subsolar merger events, the 2025 detection will stand as the initial confirmation of a universe structured by primordial black holes.